One often hears of the expression an exponential increase. The cost of health insurance in a certain country increased year on year according to the relationship given by y equals a times b to the power of t, where y is the annual cost of insurance in euro and t represents the number of years since 2006. This is an exponential relationship. Okay, so I covered functions of this type in a previous video. We want to show that y equals a b to the power of t may be written as log to the base 10 of y equals log to the base 10 of a plus t log to the base 10 of b. Now we saw that in the previous example, in the carbon dating example actually, where the log of both sides of the exponential function was taken. Now in this case we're taking log to the base 10 of both sides. So I take log to the base 10 of y, and that must equal log to the base 10 of a times b to the power of t. In the carbon dating example we took log to the base e or ln of both sides, but it's the same idea as here. We'll be applying the same laws of logs. As you saw before, we have a product here, and the log of a product is just the sum of the logs of each part of the product. So we have a multiplied by b to the power of t, so we have to get the log of a plus the log of b to the power of t. Next we use another law that tells us that if we have log of something raised to a power, we can multiply that power in front of the log term. So we can write this as log to the base 10 of y equals log to the base 10 of a plus t times log to the base 10 of b. Now this here is a linear relationship between log to the base 10 of y and t. Okay, you know, this is the dependent variable, which in coordinate geometry is the y variable. The independent variable is x, so x is t in this case. This is just a number, so this is just a constant. This is like a constant times x, so that's your mx. So this will be the slope of the line, and this here is just a constant. It's just a number out on its own, and that's the number c in the general equation of a line, y equals mx plus c. So if we were to draw a graph of log to the base 10 of y against t, we would have a straight line. A straight line with a slope of this value, well, whatever b is, we have to be given b, and the intercept on the vertical axis of log to the base 10 of a. Again, we need to know a to get this number. The cost of health insurance in a certain country increased year on year after 2006 as shown in the table below. Fill in the last row of the table, writing each value to 2 decimal places. So again, this is like the carbon dating example. We have to calculate the log of a set of numbers, and the difference here is we're getting log to the base 10 instead of log to the base e or ln. So the log button on the calculator means log to the base 10. The subscript 10 is not shown, but that's what it is. So we want a log of 500 to 2 decimal places. To 2 decimal places we get 2.70. Now let's look at a graph of log to the base 10 of y against t. So on the vertical axis we have log to the base 10 of y, on the horizontal axis we have t. So these are the points, and as you can see it looks like they lie roughly on a straight line. Now they won't lie exactly on a straight line because of rounding error, and that also because y won't exactly follow an exponential relationship. We're going to use the exponential relationship to model y, but we expect it to be quite close. So if y has the form a times b to the power of t, or very close to it, then log to the base 10 of y should be a line, as we've seen earlier, and indeed it is. If you plot the points you get something very close to a line, but not exactly a line. If I try to draw a line through all of these points, I won't fit through them all, but it's pretty close. So I'm going to write this in next to my estimate for the line. I'm just going to rearrange it a little bit and have the t term first and this constant term after it. So I've written it like this. So now we can compare it more clearly to the general equation of a line, y equals mx plus c, as I mentioned earlier. So the dependent variable is not y in this case, it's actually log to the base 10 of y, and the independent variable is not x, it's t. Now we want to find log to the base 10 of A and log to the base 10 of B. Well, this is like the carbon dating question, and like what I said earlier, the coefficient of the independent variable is the slope of the line. So if we can get the slope of the line, we have log to the base 10 of B, and this term here is C. This is the y-intercept of the general equation of a line. So it's this value here. This is the value of log to the base 10 of y when t is 0. If we put 0 in for t or 0 in for x, you just get the constant term. Actually, I'll start off by getting log to the base 10 of A. So we'll try and estimate it from this graph. So you can draw a line of best fit as best as you can through those points, and see what you get here. So this is very close to 2.6. So that's what log to the base 10 of A is. So how do we get A from that? Well, we just put 10 to the power of 2.6. Now to the nearest whole number, this is 398. Next we get log to the base 10 of B by getting the slope. So I'll pick the points that are closest to this line. I'll pick these 2 points here. So I'll get the horizontal difference between the points. I'll go from starting with this point, I'll go along horizontally to here. So delta x, or the change in x, will be +2, and then we go up a distance delta y, and that's going to be positive as well. So this line has positive slope, as you can see. Delta x is not +2, it's 2 minus 1, which is 1. Delta y is 2.79 minus 2.7. That is 0.09. So the slope is delta y over delta x. It's going to be positive. 0.09 divided by 1. Well, that's just 0.09. So the slope is the coefficient of the independent variable. It's log to the base 10 of b. So how do we find b? Well, we put the base to the power of 0.09, and that gives us the argument, which is b. So b is 10 to the power of 0.09. To 2 decimal places we get 1.23. What was the cost of health insurance in 2006? Now, the independent variable is the time in years. It is the number of years after 2006. So number 1 corresponds to the year 2007. Number 2 corresponds to the year 2008. So these are the number of years after 2006. So this is the cost of insurance. The cost of insurance 1 year after 2006, namely 2007, can be worked out but from the coordinates of this point. Well, log to the base 10 of y, it will give you 2.7. So obviously this here must be 2006. So we just extrapolate back 1 year. Remember, y is the cost. So we have log to the base 10 of y equals 2.6. So we have to find y for that year, but we've already done that. We've calculated it here. It's just a. It's just 398. Log to the base 10 of y, or a, is 2.6, so a or y is 10 to the power of 2.6. Find a time t which will give a cost of 2,200 euros to the nearest year. Now I'm going to go back to the original equation, the exponential relationship between y and t. And we found a and b. So I've just plugged in for a and for b. So y is the cost, so we want to set y equal to 2,200. So all of this is 2,200, and we need to solve for t. So we start by isolating 1.23 to the power of t. So we just divide across by 398. Now how do we get at t? Well, t is an exponent or a power. To get at that, we have to get the log of both sides. So you can use log as in log, that is log to the base 10, or you can use ln. I'm using ln here, it doesn't matter, because one of the laws of logs is that we can bring the power down. That's the idea of taking the log of both sides. Bring the t down, and Then I've divided across by ln 1.23. So plug all this into the calculator to get t. Solving this to the nearest year, you get 8 years. So remember, this is the number of years after 2006. So if you want the exact year, you'd have to add 8 onto 2006 if you just want the year. The value of t is 8, that's the answer, but if you just want the year, you get 2014. Here's the graph of the exponential function. When t is 0, y is 398. That's this point here. And of course, since the power is positive, we have an increasing function of t. So here we have the graph of y against t. So the 0 corresponds to the year 2006, and each of these numbers is the number of years after 2006. So 1 is going to be 2007, 2 is going to be 2008, and so on.